Okay, good afternoon. And I hope all students should have an entrance card and signed in. Okay, and if you haven't, raise your hand and one of the TAs will come around. Okay, looks like we're good. So welcome. And this is the first public climate change seminar of this year, 2023. And first of all, I'd like to thank the Department of Biological and Environmental Engineering and the Cornell Atkinson Center for Sustainability for hosting the seminar, for supporting us. Okay, so it's my great pleasure today to present Vivek. You say your last name.
Vivek Srikrishnan.
Thank you. I always mangle names. So it's my great pleasure today to present Vivek as a first speaker. So Vivek joined the Department of Biological and Environmental Engineering a few years ago in 2021. He received his PhD at Penn State in energy and mineral engineering. And as an undergraduate, he has undergraduate degrees from University of Illinois in mathematics and philosophy. So his group works to analyze strategies for managing climate risk and providing decision support for stakeholders faced with these risks. His research combines systems engineering, climate science, statistics, economics, social science, ethics, and decision science. And the research aims to improve our resilience under deep uncertainty and dynamic environmental risks. And something I just learned today is that Vivek lost in Jeopardy when he was a grad student, but evidently he came home with some pocket money, I think.
It was enough to cover the cost of the flight in the hotel.
Okay. So let's welcome Vivek.
All right, thank you, Peter. Hello, everybody. So my talk today is called An Introduction to Climate Risk Management. My hope is you can come away with a sense of what that term actually means in a certain sense, and why is this kind of, at least I think, an interesting area to work in and to think about. So broadly speaking, as an overview of the talk, so first I'll introduce myself a little more, then we'll talk about what do I even mean when I say climate risk. That should be an important thing to clarify before we talk about climate risk management. Then I'll talk about climate risk management. What does that entail? What are some of the possibilities there? How does uncertainty influence climate risk in the sense of how we assess what these risks look like and how different strategies might form under them? And then lastly, we'll do a summary and have some takeaways and discussions, hopefully. So first, to introduce myself, that came out a lot bigger than I thought. As Peter said, I joined Cornell a couple years ago. This is my second year. Prior to that, I was at Penn State, where I did my PhD and a postdoc. So my PhD was in uncertainty quantification and machine learning for solar resource assessment. And then as a postdoc, I started to move more into climate change and thinking about climate science and some of the risks there as well. And so my research now really is more on the climate risk analysis, climate risk management. Again, we'll talk about what exactly I mean when I say that. A lot of my applications of interest are related to flooding, largely coastal flooding due to changes in sea level rise, but also changes in precipitation patterns. And one of the things that I'm really interested in as well is the reliability of the electric power system under some of these dynamic environmental hazards. We've seen examples of power systems suffering catastrophic failures in the last few years due to environmental conditions. And a particular interest as well is the influence of some of the human system dynamics. So there's climate change, that's the physical system side, but things that we do on the human system can exacerbate or alleviate some of those risks and some of those impacts. And so thinking about how those responses kind of play with each other is something that I'm very interested in. In terms of teaching, in the fall, I teach BEE 4750 or 5750, which is environmental systems analysis. And in the spring, that number will probably change in the future, but it's a class actually broadly similar, diving in a little more deeply in some of the concepts that we'll talk about today on climate risk analysis. Okay, so I've said the phrase climate risk several times. What do I actually mean by that? So the way in which we might define it is risk, and I put that in quotes because that in of itself is also a word that gets thrown around a lot. Created or enhanced by the impacts of climate change. So does climate change play an important role somewhere in the risk calculation. So one of the key things here that is really critical is that there's the, as I just said, there's the physical system side, right? The actual impacts of climate change itself, changes to precipitation patterns, changes to temperatures, sea level rise, et cetera. But on pretty much every part of that equation, our socioeconomic dynamics end up interacting with that. So at warm, that has something to do with our economic, energy, et cetera, systems. And then what are the actual potential impacts? How might they actually, how are we exposed to them? That also is reflective of our broader socioeconomic dynamics. So there's this rich kind of interplay that results in a really interesting set of problems, I think. So to talk about what we mean by climate change, or by climate risk, this is a figure that I got from the New York Times. I think 427 is a consulting firm. They basically tried to map in some way what they thought the top climate risk in 2040 would be in different parts of the world. Now, there's some information compression going on here because you rank and you show what the top is, but there could be others, right? Along certain coasts, it doesn't mean that flooding is not a common thing. It doesn't mean that droughts and heat waves are not co-occurring, but this is just a way to show that there's a lot of different colors up there. I apologize for how small that legend is. But flooding, heat stress, water stress, wildfires, hurricanes, sea level rise. So there's a lot of different impacts which are exacerbated or where the dynamics are changed due to the impacts of climate change. Not only that, but these are getting worse over time. I can remember, I'm sure Peter can remember more acutely, a time when people sort of treated climate change as if it was almost a science fiction-y problem, where these are concerns that we might have, but really the really major impacts aren't going to happen for decades from now. So why overly stress? And the reality is that we're seeing that a lot of these impacts are occurring more frequently. They're becoming worse, kind of year by year almost. So these are just a few headlines taken from just the last few weeks of coverage related to environmental hazards. There's the atmospheric rivers that are causing major flooding in California at the moment, right? And otherwise, California has a frequent drought problem. Wildfires as well are a common problem out west in California, elsewhere. Australia, right, a few years ago, suffered really catastrophic wildfire. For people who live on the coast, sea level rise is really worsening the chances of flooding and damages. And then more broadly speaking, we can kind of start to identify, and researchers have done this, the fingerprint of climate change on more extreme, whether that's heat waves, extreme precipitation, extreme drought, et cetera. So this is something that is becoming more and more pressing, in the near term, to kind of get a grip on what do these risks look like and what can we do about it. So, and you can see this also in the number of firms that have popped up recently. There's a lot of companies that brand themselves as climate risk analytics or climate risk firms, right? And they do a lot of different things. It's almost a cliched buzzword at this point in for a lot of these companies. And so one of the things that I hope to do here is to put that on kind of a more foundational setting. Like, what do we actually mean? Is there a principled way to talk about this versus there are bad things that happen from climate change? So to do that, first, let's talk about what we even mean by risk in the first place, right? Because this is a word that has a few different uses as it gets used colloquially. So intuitively, we can think about risk as the possibility of loss, damages, or harm, right? If there's a possibility that something bad is going to occur, there's a risk of that occurring. And the size of the risk is proportional to either the probability of the hazard or the damages from that event, right? And usually we really focus a little bit more on the damages when we talk about a high risk, right? I have a high probability of stepping off a curb wrong and rolling my ankle, but that's not really that damaging of an impact, right? So I don't really talk about that as a high risk event. Whereas events that have lower probability and higher damages are often what are in the back of our minds when we talk about risk, right? These are usually extreme events that could have a really negative implication. But either way, we generally don't talk about risk for good or neutral outcomes, right? I don't talk about the risk of my winning the lottery, right? There's a chance I win the lottery, but I don't talk about it as a risk, right? That's not well, it could be harmful, but it's not usually thought of as a harmful thing. And things that are deterministic. So if I know for sure that something is going to occur, we don't say that there's a risk of that occurring because it's just going to occur, right? So deterministic outcomes are not usually considered as part of risk. And so therefore, that means that uncertainty ends up playing a really important role. And that's a large part of what I'm going to talk about today is the role of uncertainties in this process. So here's a couple of cartoons about risk, just to kind of lighten the mood a little bit. So this is from Saturday morning breakfast cereal. I don't think it's phrased in an ideal way. This is why people should learn statistics. But basically, you have somebody saying we should take any action and pay any cost to limit the risk of a terrorist attack, right? These are things that don't occur very frequently. They are high damaging when they occur. Would you like to add safety features to your car? No, it's too expensive, even though car accidents occur much more frequently than terrorist attacks, right? That's kind of something about weighing, how we weigh different risks. Right, and then here's another, this is from XKCD. One person says we should go to the North Beach. Someone said the South Beach has a 20% higher risk of shark attacks. The person in the middle says, yeah, but statistically taking 3 beach trips instead of 2 increases our odds of getting shot by a swimming dog carrying a handgun in its mouth by 50%. Right, and then the person in the beret says, oh no, this is our 3rd trip. Right, and so this kind of gets to what's called the base rate fallacy, which is you can talk about percentage increases in something happening, but a 50% increase of a very small thing is still small, right? So this is where kind of understanding what the likelihood of that outcome occurring, the probability of that occurring matters, not just what is the percentage of an increase or a trend. Okay, so back to risk. So the common framework that gets used, so this is the definition used by part of this is the definition used by the Society of Risk Analysis. It's also a framework used by the Intergovernmental Panel on Climate Change as well in their reports when they talk about climate risk, is that risk is a combination of hazard, exposure, and vulnerability. So by hazard, we mean what is the bad event that is occurring that has some probability of happening. So that could be a flood, earthquake, volcano, heat wave, anything of that sort. That is the hazard part of the equation. Exposure is how many people or what assets or whatever is of interest is subject to the impacts of that hazard. So how many people live in the floodplain, for example, right? That's an example of exposure. Those are the people who could suffer negative consequences from that event occurring. Vulnerability is for the people who are exposed, how damaging would that be? So, you could, for a flood, vulnerability could be, do you have a basement that you store lots of stuff in, right? Versus is your first floor just a parking garage that water can just kind of move through, right? Those are different vulnerabilities, even if both people are exposed to a flood in the same way. And the last piece of it, which this is a relatively new contribution to this framework, is the idea of adding human system response as well as a way that can alleviate or exacerbate some of the other pieces here. So to think about something that at least was until recently fresh in all of our minds, let's think about what is the risk associated with ending in the hospital because of COVID-19, for example, as an example of how we might decompose that risk into these different pieces. And one thing I want to stress is that this is not a framework that gives you a unique separation. Exposure, has vulnerability, response. These are all different moving pieces you could classify in different ways. The goal here is more to think about this in a really structured piece and how there are these different entry points for some of these changes to occur. So for example, the hazard would be, well, you get exposed to COVID-19, right? You're around people who are shedding the disease and you catch it. That's the hazard that would trigger the risk of ending up in the hospital. Exposure, again, would be who are you around, right? Are you around people who are shedding the virus? To what extent? Vulnerability, we know there are certain conditions that make you more or less vulnerable, age, cardiovascular health, et cetera, that may make you more or less vulnerable. And then response could be, well, how is your behavior changing? How are other people who may be sick? How are their behaviors changing in a way that might change how often you're exposed or to the disease? So you can kind of think through these in some ways, but again, I want to stress this is not a unique thing. It's more of just a framework for how to think through these problems. So then back to the definition of climate risk, where climate risk refers to changes in risk that stem from the impacts or response to climate change. So, so thinking about this in how this might enter some of these, this framework in different ways, if we think about changes to hazards, right, drought or flooding, that could be changed by the impacts of climate change, changes to extreme temperatures, extreme cold, and extreme heat. Sea level rise, right, that's another hazard that can change the impact of flooding or various other impacts. And then there's lots of others, right? I was sort of limited by space, but you could keep going down the list, right? There's very few parts of our planetary system that are not impacted by the climate in some way. Then when we think about, and often people stop there, right? When they talk about risk. Sometimes they say the risk of sea level rise, right? When really they mean the probability of sea level rise or the level of that. So they're sort of using it just to refer to a change in the hazard. But more broadly, we can also talk about the ways in which climate change interacts with different changes to exposure or vulnerability. So if climate change creates more compound events, so events that occur one after the other, that then would weaken the resilience to some of those subsequent events. If you're still recovering from a flood and then you get hit by an earthquake, right, that could be a bad thing. And so that could reduce the vulnerability, increase the vulnerability, decrease resilience. So that's a way in which by making these events occur more frequently, climate change can weaken, can increase the vulnerability of the system. Changes to urbanization or land use land cover can also interact with climate change and sometimes be driven by some of the climate changes as well, depending on the regions that are impacted by certain things. So these are all ways in which climate change can enter into the system, right, and change the different parts of this calculus. It's not only about changes to the physical hazards themselves. So a lot of the motivating questions that I ask and that other people who study climate risk ask are, so one, what are the potential impacts of climate change, right? What are those hazards in the first place that we're talking about that might change some of these? Another is, what can we say about their uncertainty? So a really critical part of that, right, is that risk is something that is probabilistic. It's something that is, and that there are uncertainties that impact what those impacts look like, how likely are they to occur, and how likely is what is their intensity likely to be. So all parts of that, the hazard, the vulnerability, exposure, they're all uncertain in certain ways. And then lastly, what are the impacts of those uncertainties on the performance of risk management strategies? So we could have different interventions that all might do something, but they all might have vulnerabilities to certain changes. And if we don't really understand what those uncertainties look like, we may not match the risk management strategy with the way in which the system might progress in the future. So how can we assess the potential failure points of different strategies? How do we understand what those might look like so that we have enough time to kind of change course? Okay, so that's what I mean by climate risks. Now, what do I mean by climate risk management? So this did not turn out as sharply as I had thought. Okay, so I will give a summary of this figure, but basically this is an overview of kind of the feedback loop for the climate system, and then also the way in which the climate risk management strategies kind of enter into it. So roughly speaking, we could think about it this way. We can sort of start here. Let's say there's some economic output that causes the emissions of greenhouse gas right through that activity. That causes a change in greenhouse gas concentrations. That changes the radiative forcing, right? So the amount of warming that can occur. That changes the climate through that impact of that change of radiative forcing. And then that change in climate, there's some impacts that are caused as associated with that. So if we think about it in the system, the pluses and the minuses are just showing whether these are amplifying or reducing influences. So, increased economic output usually results in more greenhouse gas emissions. More greenhouse gas emissions increases. So around the loop there, the plus or minus between climate impacts and economic output is that there are some parts in the world. This is an argument that some people in Europe make that that certain areas that are colder become warmer and therefore are capable of more agricultural yield, for example. But for quite a bit of the world, right, it's a negative. It can be a negative impact. So then the strategies, broadly speaking, we can kind of categorize a lot of these into several buckets. The first is mitigation. So this is acts which are reducing the emissions of greenhouse gases. So those enter into the greenhouse gas emissions part of the equation. So changes in technology, changes in energy use, et cetera, which result in reducing the intensity of CO2, methane, et cetera, emissions into the atmosphere. There's solar radiation management. So that is over here. That changes the radiative forcing. That's the idea of injecting aerosols into the atmosphere to increase the absorption and or reflectivity of incoming solar radiation. So this basically, you're not changing the greenhouse gas concentration and sort of that blanket over the planet. You're reducing how much of the solar radiation penetrates, gets to that point. So this is something that you may hear a lot about in the news. There's actually a lot of like tech firms and tech money that's kind of going in that direction. I'm just listing it here. I have thoughts about this, but I'll be neutral at the moment. And say that fits into the radiative forcing piece of it. So it doesn't affect the emissions, it doesn't affect greenhouse gas concentrations, but it changes the actual radiation forcing the climate system to change in a certain way. Adaptation is there as well. That changes the impact. So that's like building a levee to protect against flooding, hardening, elevating homes, right? Those are all adaptive responses. So that doesn't change what the impacts look like. It just hopefully addresses kind of the exposure vulnerability, different pieces there. And then carbon sequestration is another that is aimed at changing the greenhouse gas concentrations. That's something like a negative emissions technology or direct air capture, which is aimed at kind of sucking CO2 out of the atmosphere and putting it in the ground. So you may be emitting the same amount, but you're trying to capture and store it instead of letting it change the radiative balance of the planet. So one of the key things here is that these all work on different scales, right? They have different timelines in which they work. They work on different spatial scales as well. Mitigation is something that, really is a planetary thing, right? This is a global thing where everyone contributes in some way. It also is totally unclear without, except for a total cessation of emissions, what the timeline looks like on which you would start to see kind of the unraveling. There's a certain inertia in the climate system where a reduction in greenhouse gases doesn't necessarily mean an immediate response in warming. Solar radiation management works pretty rapidly. The problem is if you disrupt radiation, because all you're doing is kind of masking the amount of greenhouse gases in the atmosphere from occurring, there's what's known as a rebound effect, where the rise in temperature following a cessation is likely to be much more rapid than it would have been in the first place. And that could be destabilizing potentially, right, depending on the system that you're talking about. So, but that kind of works globally and it works on basis. Adaptation is fundamentally local, right? You're talking about something that is happening on a local scale. So that is something where you're kind of catching up to what you think the impacts will be, and you're doing it in a local place. You're not actually changing the sort of global balance of things. And then carbon sequestration is, again, something you kind of put in a local place. Maybe you could scale that up, but it's something that is kind of occurring. Like there are some small scale power plants that do this. I think Britain has a couple of demos, but again, it's kind of a local thing. You put in like a site installation. So these occur, and again, just like with mitigation, because you're changing the concentrations, it's not totally clear on what timeline you actually start to influence things. But broadly speaking, we can probably think about this, there might be more, but we can broadly think about these buckets of ways where you can intervene in this feedback loop by which we cause climate change and it causes impacts and risks. So again, each of these strategies is subject to different uncertainties as well, largely because of the differences in scale that they operate on. So for adaptation, we need to know something about, for flooding risks, what does sea level rise and flooding hazards look like, right? If I'm going to build a levee, it's good to know what that height looks like. What am I aiming towards? Is that even feasible to have a levee that large? What might that impact look like? What might the failure look like? I can't assess that without knowing something about those hazards, and that's an uncertain thing. From a mitigation side, how long will it take for the climate system to respond to a reduction in greenhouse gas emissions, right? Mitigation is not necessarily something that you start because next year you can't tolerate any more warming, right? There's some lag in that response. And so that would affect how you roll out mitigation and at what point do you expect that you need to still continue to adapt. For sequester CO2 or for sequestering or mitigation, you might say what technologies might emerge to do that more effectively, right? That's a key question. And so these are all examples of some of those relevant uncertainties. There's questions about technologies, there's questions about economic growth. There's all sorts of different issues here. And so one of the cases that I want to make here is that uncertainty really plays a critical role in anything that we talk about with climate change in terms of what the impacts might look like and what we might want to do about that. So let's talk about what do I mean by uncertainty and how does that impact decision making and how we think about decisions. So uncertainty can enter into that hazard, exposure, vulnerability response model in a few different ways. So the hazards themselves are uncertain, right? We don't necessarily know what sea level rise will look like, what extreme changes in frequencies of extreme cold that might cause the natural gas pumping system, like what happened in Texas a couple years ago, to seize up, right? How often will those occur? That is uncertain, right? That's uncertain for a few reasons. It's also so that there's just some variability within the climate system itself. And also, we don't know how many more emissions we're going to be dumping into the atmosphere in the future, right? That's an uncertain thing as well. Model estimates of any kind of exposure or vulnerability, right? That itself, there's uncertainty there as well. When I run a model, how am I forcing it? How am I specifying my model? These are all things that have uncertainty themselves. And then uncertainty in the human system response. Can we necessarily predict how humans will behave under certain stressors? So there was a big media report that came out from one of these climate consulting firms a few years ago, I can't remember which one, that estimated something like by 2050, half the world's population is going to flood or like be exposed to flooding. And the answer is that's probably not right, because in general, though Miami is doing a pretty good job of trying to convince me otherwise, people don't tend to just sit there and let themselves get flooded, right? You move, you adapt in some way. That risk is not exactly as kind of portrayed in that really simplistic analysis. So all of these things are uncertain to some degree. And those uncertainties, in some cases they might wash out, right? In some cases they might not. In some cases they may actually really shift the projection or what we end up with. So what do I mean by uncertainty? So glibly, I could say uncertainty is just a lack of certainty, right? Less glibly, if I can't accurately describe current or future states, so if there's something about the current condition I can't describe, or if there's multiple possibilities for how the future might unfold, we could refer to that as uncertainty, right? Both of those cases there. So it's a deviation from determinism and knowing exactly what the process is. There's a almost certainly apocryphal story about the mathematician Simeon de Laplace, who you may have seen his name, where he wrote, he was a big supporter of Napoleon's. He wrote his book on like celestial mechanics, and Laplace had a very deistic view of the world. The idea is that the universe is just kind of a clock. You just kind of wind it up from some initial state and let it run, and everything can unfold. And our only limitation is the lack of knowledge, right? So there, the uncertainty is not in sort of the evolution, right? He thought you could, in principle, describe everything unfolding, but you don't necessarily know to appropriate precision those initial conditions, right? And so we can, that's a particularly strong viewpoint, right? But either way, even with that, about as deterministic as you can get of a worldview, there's still a fair amount of uncertainty involved in that process. And so uncertainty factors in the risk in the following way, which is that if we think about the probability of events, right, we can think about a couple of different risk profiles. And this gets back to the example of what happens if I roll my ankle, right, versus a plane crashing. Risk profile A, there's a lower probability of some low damage events, but a high probability of extreme events. And for risk profile B, there's a higher probability of more moderate events, but the more extreme events are less likely to occur. And one of the things that we see with climate change is a higher frequency of those extreme events occurring, right? That's the typical thing that we tend to observe when we look across a number of different types of hazards, is the shift from sort of risk profile B, where you might get these small events, to ones that are more extreme, even if they occur less frequently, and that they start to occur more frequently and they're more damage. So another key thing here is that there are many different uncertainties relevant to climate risk, right? We've got hazard, we've got vulnerability, and we've got response. So there's a lot of different things and a lot of different moving pieces here. So I've got a little poll if you want to participate in it, just asking to brainstorm what are some examples of some relevant uncertainties that I think, and let me know if I have not properly activated that, because that's been a thing before. Okay, so for a few, we've got sea level rise. Yeah, so there are different dynamics relevant to the amount of sea level rise. Ice sheet behavior, for example, is one. The amount of warming or the policy targets. I think policy was also one that was up there. That certainly is one that just the amount of emissions, right? And our transition towards reducing emissions, that is a relevant uncertainty. Yeah, so we've got a bunch of different system things related to very specific hazards. Food security, financial burden, agricultural impact, future emissions, amount of precipitation, human behaviors, how human diets will change. Yeah, a lot of those are good. That's quite a few negative and positive feedback loops. Yeah. So those are good and much broader than the list that I briefly had here. So I kind of separated them into geophysical and socioeconomic uncertainties, which I think were reflected by that list, right? That you were also thinking in the same broad direction. So I think Peter said you talked briefly about some of these uncertainties. So climate sensitivity, this is right, equilibrium climate sensitivity, the equilibrium amount of warming that occurs from doubling the amount of CO2 in the atmosphere. That is an uncertain quantity because we don't have an experiment, right, where we have doubled the amount of CO2 and run the Earth for that long to see what happens. The amount of ocean heat that the ocean absorbs, how rapidly that diffuses into the lower ocean, right? The ocean is a massive heat sink. And in fact, often when you see little plateaus in the amount of atmospheric warming, ocean warming is continuing to increase. Aerosol scaling, so this is the amount of cooling associated with an increase in the amount of aerosols in the atmosphere, because aerosols either absorb or reflect back the amount of solar radiation. And then I just threw another one, changes to things like tropical cyclone intensity. So that's a little more downstream, right? But things like are hurricanes becoming more strong or becoming stronger on average, that is still something that we're still kind of looking at. On the socioeconomic side, economic growth, right? How much will the global economy grow in the future? How does that translate to increased emissions or the amount of emissions in general, right? Of course, that's totally unknown, right? You can't forecast, you can't predict that. Things like technological changes, we certainly know that that's not something that's very easily predictable. Population changes, these are all things that are relevant to the amount of emissions and therefore the amount of warming, but they're all things that are very uncertain. But if you actually want to get a sense of what future impacts might look like, what global warming might look like in the future, you need to have some way to start thinking about what these uncertainties look like. So broadly speaking, we can split these uncertainties, and I've kind of alluded to this indirectly in that last slide, into two broad categories. First, there are probability distributions for which we can broadly agree, or there are uncertainties for which you can broadly agree on probability distributions. We can estimate, for example, a probability distribution for climate sensitivity based on historical levels of warming and historical records of CO2 emissions. Right? We can get a sense of what that looks like, what that range looks like. But then there's others for which we cannot possibly do so, right? Again, future economic growth, future emissions. If I ask everybody in this room, by what percentage will the global economy grow in the next 100 years, or how many more CO2 emissions will we emit in the next 100 years, I will probably get as many different probability distributions as there are people sitting here, right? There's no clear consensus. It builds in a lot about your worldview and your assumptions that go into it. So we can break this into a taxonomy of what you might call knowns and unknowns. And I'm using that language to suggest a famous press conference that Donald Rumsfeld, who was the US Secretary of Defense when we invaded Iraq back in 2003, gave, where he kind of went on this little rambling thing about how there are known unknowns, there are known knowns, there are known unknowns, and there are unknown unknowns. It turns out there was some logic there. This is something that Nassim Taleb has also talked about in the concept of black swans as well, where we can actually map these concepts onto reasonable notions of uncertainty. So by known knowns, these are things that we know for sure, right? These are things that are certain. Known unknowns are what you might call shallow or well-characterized uncertainties. So these are things where you know they're unknown, but you can write down a probability distribution for them, and you can generally have confidence that that probability distribution reflects things. So that's like saying, the known known, that's saying I've already rolled the dice. What is the value? The known unknown is I know I have a 6-sided dice and I roll it. Well, I know I've got a 1 in 6 chance of any particular thing occurring. But then there are unknown unknowns, which are things like future economic growth, where I know I don't know them, but I also don't know how to characterize what they might look like in the future, right? What do those ranges look like? How likely are they? That's akin to, first, you're going to grab a die out of a bag, or you don't know how many sides are on the dice. What do you think the probability of getting a 6 is? Right? It could be 0, right? It could be a dice that has 4 sides. It could be, 1 in 20. It could be something, right? There are a lot of different dice shapes out there. And so the probability of getting any particular thing is going to depend on that, right? It's sort of conditional on that expectation, on that value. And so there are things that we don't know the probability of, right? But they are unknown. So using this framework, climate risk is subject to a mixture of both shallow uncertainties and deep uncertainties, right? There are some uncertainties where we can write down a distribution, and there are some where we cannot. And it actually ends up mattering quite a bit which ones correspond to which kind of category. So some of these are, oh, that drained a lot more rapidly than I thought. Okay. Yeah, a plug. Yeah, thanks. So for example, climate sensitivity, like I said, there's a probability distribution. This is taken from the most recent assessment report from the Intergovernmental Panel on Climate Change, showing what values of climate sensitivity are more or less likely in terms of consistency with historical records. So we can actually get, and this has been an actually fairly stable distribution over decades because there is a lot of data on this. Now, that doesn't mean they're easy to deal with. So the geophysical uncertainties that I mentioned before are really highly correlated, which means they tend to vary together. They're not just independent things. So for example, climate sensitivity, this is from a paper that I was on a few years ago, or a couple years ago. The climate sensitivity, as it increases, there's not a uniform scattering of either the ocean heat diffusivity, which is the color coding, or the aerosol scaling factor. The reason for that is that let's think about what happens with a really high climate sensitivity, right? That means that a certain amount of CO2 is expected to produce a really large amount of warming. That heat would have to go into the atmosphere to be consistent with the amount of warming that we've seen with the CO2 emissions historically. And there is not, if you look at records for ocean heat, it does not look like, that has to be really high. So we tend to get these really high colors, right, up in the high climate sensitivity range, whereas in the lower climate sensitivity range, that's as you don't expect to see as much warming. And so you don't get as much, there's less of a constraint on the ocean heat uptake because the ocean doesn't have to whisk away as much. So it could be higher. And similarly, there's a nonlinear relationship. You kind of get this banana shape with aerosol cooling as well, where the idea is if you had really high climate sensitivity, you would also need not only really high atmospheric or really high ocean heat uptake, you would also need aerosols to actually exert a really strong cooling influence on the planet. And similarly, if aerosols had too large of a cooling on the planet with a low climate sensitivity, that would predict less warming than we've actually seen. So you can kind of tease out some of these nonlinear relationships. The other one I didn't talk about here is carbon sinks. That was another, I saw that as one of the uncertainties. But how sensitive is the rate at which carbon sinks, like big forests, take up carbon? That is dependent to some degree on the temperature. And so what does that look like? That also is related to this process as well. So so these are really nonlinear, and it actually turns out, and I'll give you an example of how this matters. Actually, I think I might have that next. Yes. So it turns out that if you account for these calibrations for these parameter relationships, that is the orange distributions in the orange region here. This is past temperature anomaly and then future projections going up to 2200. And then these are just little snapshots of the distributions that you might expect in 2050 or 2100. The gray line is what happens if you ignore those relationships and you just treat these as if they're independent, which is currently what the US government, the EPA, does, right? They actually do that at the moment, where they treat these as uncorrelated. Thank you. Sorry, a little bit of a brain fart there. And so these are all the data points, and we can see that actually they're pretty consistent. But then as you start to get around 2000, there's been enough emissions that you do really see a separation. And in fact, you would expect to have a much longer upper tail. And that's because of you're sampling from areas where you get things like really high climate sensitivity and really low ocean heat diffusivity that are inconsistent with the past record. But if you combine those and expose them to a high amount of warming, you end up here in this region that actually may not be as plausible. So this matters from a risk perspective because we want to get a good sense, a realistic sense of what the impacts might look like, right? And so chopping off that tail does not mean that climate change is not serious, right? But it gives us a sense of how we might want to allocate resources, right, accordingly. So those are the shallow uncertainties, and again, they matter and they can be really important to characterize well. But then there's also the deep uncertainty. So these are the unknown unknowns. So you talked last week about the RCPs and the SSPs, the scenarios of future emissions and socioeconomic growth that are used to guide a lot of the impacts and mitigation analysis. Again, good luck finding consensus on those, right? Again, if I asked everyone in the room to draw a probability distribution over this, I probably would get that many different distributions, right? One for everybody in this room. And there have been some really good actual psychology experiments and judgment decision-making experiments on how plausible people think each of these are. And this has actually been somewhat of a controversial thing recently, so much that it did show up in the assessment report over whether this high SSP5 8.5 marker should be included in analyses at all, right? Just because it is up there, and we are likely to be on a trajectory that's more moderate. Though again, there's a lot more to say about that in a different talk. So why does this matter? So let's look at an example of what's called the social cost of a greenhouse gas. So this is a tool in the regulatory arsenal. The idea is the US government, any kind of environmental regulation that occurs, you have to do a cost benefit analysis. That's been, ever since the Reagan administration, a requirement. So the EPA has to justify the benefits of an environmental regulation versus the cost of complying or the potential economic damages associated with that. The problem with climate change and with a lot of things related to mitigation is that the benefits are really far in the future, right? Whereas the impacts can be felt today, right? The economic things, what does it mean to upgrade your power plant, right? To emit less, that costs a lot of money today. Whereas the benefits from that may not be realized until decades or potentially even centuries from now. So because we have a time preference, and this is reflected in a lot of the calculations, right? I would rather have $1 today than $1 10 years from now, right? For a number of different reasons that go into that. We tend to over discount the amount of value from these future changes. So the social cost is a way of quantifying how much harm over a time horizon is caused by emitting 1 ton of a particular greenhouse gas, right? So that's a concept of the social cost. The EPA basically looks at what is the relative, balance of that, and then they can try to justify a regulation accordingly. So this actually goes into all of the different aspects related to climate change regulations. In fact, one of the things, I'm hopefully not shattering any bubbles here when I say that the Trump administration was not a fan of climate mitigation. So one of the things they actually did was change the way in which the EPA calculated the social cost of greenhouse gases to try to make regulatory actions more likely to fail a cost benefit analysis, right? This is a really critical thing in sort of the accounting of the way the US government works. So from this recent study, this is that same Erickson et al. Study that I looked at before. If we look at the joint distribution of those well-characterized uncertainties, so looking at those relationships that we saw how that cut off that tail, that reduces the government estimate by about 22% of the social cost of methane in particular. So methane is a particularly potent greenhouse gas, but it decays into CO2 after about 12 years. And so it actually does reduce it because you chop off those really extreme warming outcomes where you're more likely to trigger things like the melting of the Antarctic ice sheet, like the total collapse of the Antarctic ice sheet and massive sea level rise as a result of that. It still is a very high level, but it's just a little bit lower. And it turns out that switching the radiative background forcing from RCP 8.5 to RCP 2.6, so this is from the extreme high to what used to be the extreme low version to get a range, also reduces the estimate by 24%. But whereas we can say that this makes sense here, right, because we know something about the physical system and how it impacts those uncertainties and that reduction, who can, there's again this element of subjectivity to say, do we think that RCP 8.5 or RCP 2.6 is more likely, right? That's actually something that you have to argue and kind of defend, and it's not clear why one should necessarily pick one versus the other, right? There's a lot built into that. And so this gets back to this issue of how complex decision-making can be in the presence of these deeper uncertainties, when you don't have a distribution you can point to say, yes, that's the answer. So this type of complication can lead to inconsistency when it comes to assessing risks or making bets or assessing probabilities under deep uncertainty. So to see this, I want to talk about an experiment that was conducted by Daniel Ellsberg, who was a famous psychologist back in the 60s. And he did what he played two different games with his experiment, or with his experimental subjects. One was a 2-urn game. So consider 2 urns, each containing 100 balls. Urn A has 50 red balls and 50 black balls, so evenly split. Urn B has red and black balls, but you don't know how many. Okay, so subjects were offered 4 different bets. Bet 1A, you get $1 if you draw a red ball from urn A. Bet 2A, you get $1 if you draw a black ball from urn A, and similarly for urn B, right? 1B is you draw a red ball from urn B, 2B is you draw a black ball, and you get $1 depending on how that turns out. So we may not have time to actually go through polling and everything, but let's just ask, in general, do people have a preference between 1A and 2A? Which would you prefer to bet on, if either?
Can you put back to the choice?
Yeah. So between, So between 1A and 2A, do you have a preference? No? Okay. How about between 1A and 1B?
Yes.
What would be your preference? 1A? Okay. That's exactly what Ellsberg found as well, that there was no difference between 1A and 2A, but there was a preference for 1A and 1B. The reason why that's interesting is that there's no reason to suspect that urn B is rigged against you. There's also no reason to suspect that it's not, right? So this is commonly interpreted as an aversion to making decisions under deep uncertainty. You would rather just not take the chance that it is rigged against you if you can do a known probability thing. Even though on average, if you think about all the possibilities that could occur, it's the same. So this is something that we see. People generally try to shy away from making a decision in the presence of deep uncertainty. It's a kind of a paralysis. When you can't kind of weigh what you think is more likely or another, you end up trying to make another choice. Okay. The second game that he played was called the 1-urn game. So now there is 1 urn and there are 30 red balls, and the remaining 60 balls, actually I think that should be 70, but it doesn't really matter, are black or yellow, but you don't know how they are split. So bet A is you win $100 if you draw a red ball. Bet B is you win $100 if you draw a black ball. Do you have a preference between bets A and B? A. Okay. Bet C, you win $100 if you draw a red or a yellow ball. Bet D, you win $100 if you draw a black or a yellow ball. Do you have a preference between bet C or bet D? Okay, I'm hearing C's and D's. So what Ellsberg found is that people generally preferred, just like you did, bet A to bet B, right? So they preferred taking the known there are 30 balls versus I don't know how many black balls there are. But they also preferred bet D to bet C, right? Which some of you did and some of you did not, okay? Now, the reason that that is unusual is that the preference for bet A over bet B means you think there are more red balls than black balls. If you take kind of the classical approach to decision making, you think you have a higher payoff percentage. But then you should pick bet C because the yellow balls are the same and the difference is just the red or the black. And if you already think there are more red balls, you should also pick bet C as well, right? To be consistent about it. And there's nothing that's wrong with being inconsistent. It's just, this is sort of the classical approach to decision making that economists use, for example, is that your decision reveals something about the probability that you think. And Ellsberg's observation was that, well, there's no way for that to be consistent with the broader experimental finding here, because you had this total flipping of what people thought because they were shying away from the deep uncertainty part of it. So this really complicates things, right? This is called the Ellsberg paradox because it was contrary to sort of this standard view of decision-making from economics. And it shows that under deep uncertainty, these classical approaches break down because people get uncomfortable when you don't have a probability or a likelihood, you can't compute your expectation of winning. And this heightens the importance of understanding and working with stakeholder values and thinking about alternative ways of making decisions. So maybe instead of what do you think is most likely, you might ask, what are the outcomes you'd like to avoid? And how do you ensure that you avoid those outcomes, right? Or how do you minimize the amount of regret that you might have for choosing one path versus another? But that really is actually quite a bit harder, right? There can be different objectives that different people care about, different ranges of what they might want to have or to avoid. And so this really, again, makes this a lot more complicated. But again, from my perspective, right, this makes it a lot more interesting, right? It's not as simple as I've just got a problem and I can write down a probability distribution. You actually have a lot to understand and to work with. And so like every problem ends up being a little bit different, which I think is kind of nice. So takeaways, I apologize, that was a little on the long side. Climate risk management, there are a number of different portfolios that you can consider. And I will say that one of the things that we do not do well in the climate risk management space at the moment is combining these different portfolios, like thinking about these different strategies as a joint portfolio, where you think about, well, if I mitigate this amount, how much residual adaptation is that? The reason for that is that largely we're still in this sort of scenario-based framework for mitigation, right? We don't really have a good way to kind of say, well, does that propagate out of the down? You kind of have to jump from one scenario to the next, say what those look like. Nonlinear system like the climate system, some small differences can make a big difference in terms of. So that's something that I actively spend a lot of time thinking about. Another part of the complication is that there's well-characterized and there's deep uncertainties, right? So this, how they interact in different ways are applicable to different parts of this problem, but they all kind of matter. And even the well-characterized part of the equation here is not always straightforward to deal with. It requires some decent statistical skill to kind of do some of that. We didn't talk about this, but also the stakeholder values and preferences side, the people that are actually impacted, what do they prefer? What do they want to see? What do they not want to see? We didn't really discuss that, but that really matters, particularly in light of some of the issues related to decision-making under deep uncertainty. And so the upshot is all of these make climate risk management a complex problem. And it really means that we need to be really transparent and make sure that we're doing a good job when we do the risk analysis so that people have information that they, reliable information that they can then use to make these decisions in these very complex settings. So the key challenges, I would say there's still real issues with characterizing the relevant uncertainties, right? There's still advances that we can make in terms of those, whether they're deep or shallow. Understanding how these uncertainties impact the performance. There's all sorts of modeling challenges and more fundamental scientific challenges there as well. And then how do we communicate? How do we provide decision support for decision-making given these uncertainties? One of the things that I remember the head of climate resilience for the US Army Corps of Engineers said to me once, he sort of laughed and said, I need you guys to stop giving me scenarios because I can't go to Congress with 3 possible outcomes. I have to have one. There has to be a number that she says, I need this amount of money to build this levee. It can't be, and there can't be a representation of uncertainty if she's going to talk to a congressperson, right? But there is uncertainty, right? There is actual uncertainty and it matters. So how do you strike that balance is still a really open question. So just to kind of illustrate this and the way in which values kind of end up mattering, because I didn't really get to talk about this much, but it really is important. If we think about the simple value, this was based off of an analysis in New Orleans about where do people's values enter into different parts of the system and how you weigh different objectives or different objectives, different outcomes. So we could think about building a levee or evacuation or education about what to do if there's a flood as some different things you could do. And they impact things differently. So education and evacuation, it changes vulnerability, it costs some money. So there's some issue there with economic efficiency. There's a concern about distributive justice, right? Depending on how you prioritize the evacuation, are you potentially leaving certain people kind of last in line for when they get the information? relying on cell phones sounds all well and good until you realize how many people don't have cell phones and how that actually maps to socioeconomic status. Then if you build a levee, right, that costs a lot of money, you're changing the exposure. That can also damage the sense of place, right, that somebody has. If there are people who really love looking out on the waterfront and they want to live on the waterfront, or it's a key part of the community, and you may be damaging that. That all propagates and the risks, and then there's the damages and expectation there. So these, what people prefer really can matter a lot. And so really kind of picking apart these different pieces and not just having a blanket categorization of the risk can be really important to help support that management. Okay, so thanks. Again, I apologize, that went a little bit longer than I thought, but are there any questions? Yeah.
So like, what would the day in a life kind of look like for like a climate risk management person, like when they go to work, like what do they do when they're working with the company?
So it depends.
Could you repeat the question?
Oh yeah. So I think it was, what is the day in the life of somebody who works in climate risk management might look like? And so it depends, because there's a lot of different parts of this process. So certainly one kind of line is a resilience officer for a city or for a county. And so there's a lot there thinking about, what boots on the ground, how do you make decisions about where to allocate resources, zoning, based on where you think those impacts might look like. Where do you apply for grants? That's a common thing, because often municipalities don't have the money to do a lot of the stuff on the adaptation side themselves. They need help from the US government or from state government or something to help do that. Similarly, there are going to be people in federal or state offices. So EPA, right, does a lot of the environmental regulatory actions. They have a lot of economists and a lot of climate scientists who work at EPA, or places like NOAA. Like a lot of those agencies have people who do this work. A lot of national labs do research that's relevant, right, to climate risk, to try to understand what they think the impacts are of a particular change or a particular setup. And then there's people who work directly with stakeholders, people involved in community outreach, who work to try to get a sense of what, either to raise support, increase awareness, what if you want. So it really depends on the part of it. And then again, on the other side, there's also these firms that kind of do a lot of modeling or do a lot of analysis to try to project what they think some of the risk will look like. Yeah.
So I know you kind of touched on the preferences of firms and corporations and things like that. If they're hiring someone who's doing climate risk management for the corporation, how do you think their preference to have growth and turn a profit influences their decision making?
I think there are very few companies that are going to do something that's going to stop them from making a profit.
Yeah.
What that means in terms of like what steps they can take or what they don't take is a different story, and like how much are they willing to take, that's going to depend on the culture, right? So Patagonia kind of might be at one extreme, right, where they kind of just turned over the company so that all profits go towards climate activism. Other places it might be more at the margins, or maybe if you increase efficiency, yeah, that helps climate, but also like Amazon, for example, does a lot of climate. They have a climate risk office. A lot of that is related to how do they increase the energy footprint of their computing, but that also saves them money, right? So in some cases, it's a win-win, and you can kind of brand it, right, as a climate thing. So it really depends. Yeah.
In terms of the risk framework with the hazards, exposure, vulnerability, and responses, in terms of the particularly exposure and vulnerability, is that based on the impact on humans or on the environment as well? Because I know like many people don't consider like the ecological processes as a whole as something that needs to be looked at in just like human efforts. So is that?
Depends on who you're talking to. And again, that's where I think it's a helpful framework, because you can kind of pick apart what are people including in their analysis versus just having a blanket. Here's what we think gets to risk are. You can kind of pick apart. It's a way of being a little more transparent about communicating the assumptions that went into whatever analysis you're doing. But yeah, some people do, some people don't, depending on the calculation. Yeah.
What are your concerns with solar radiation management?
So the climate system is very complex. It is not clear yet. And so, okay, I'm glad there are people who study it. I'll put it that way, because we should know what we're getting into if we go that route. But the climate system is very complex, and that's a weird point to kind of intervene, and who knows what happens. There was one set of simulations I remember somebody was talking about who, it was some place where they seeded some increased clouds, to increase that. And in the simulations, you ended up killing the Indian monsoon as like the side effect of that. So there's just a lot of complexity to the climate system and the radiated balance. So that's, I think the issue I have is I'm glad there are academics studying it and like doing the simulations, doing experiments to know what you might get. The other side of it is this threat of abrupt cessation and what the impacts of kind of that rebound effect look like. There are a lot of things that might stop you from being able to persist that until you actually mitigate. There's also the potential for the perverse outcome that people say, oh, well, now we don't need to change our warming at all. But then again, that leaves you more vulnerable for when you eventually do stop, either because of financial reasons or there's some type of socio-political shock or something that stops that from occurring. Yeah.
So given that it's important to understand some of the socioeconomic factors, do you also conduct research on the community, or like how do you understand the extent of vulnerability?
Yeah, so in some cases, there are data sets that, so like the US Army Corps of Engineers and FEMA have like building inventories. So that's one way to kind of get a sense of some of the assets at risk. But yeah, I do think it's always important, and a number of the, I work a lot with philosophers who do this and various people who are actually professionals at stakeholder engagement. It is really important to really communicate with, because these problems are fundamentally local, especially on the adaptation side, where the context of the values, the types of actions that are tolerable, and the impacts are all really fundamentally local things. And so you have to know what's going on there. The other is, it's not very valuable to do something that may address this crisis, but then like kills an economic sector, right, in an area. So you have to know what's sort of tolerable, what kind of things might people want to avoid when you evaluate these strategies. Yeah.
You talked about the impact of compound events on a system's vulnerability, but how difficult is it to predict or model like how the extent to which one event will affect another?
Very. Yeah, no, it's incredibly difficult. Getting a spatial, because one, it really depends on the way in which that occurs. So one, it's always more challenging to characterize the joint changes in probability. So what is happening to one event at the same time that another is occurring, to look at these co-occurrences. And then the other is, we're actually really not very good. And I was talking with somebody at NIST, the National Institute for Standards and Technology, about this. They're also just thinking about how do you model resilience and the recovery process, and then do you have a shock in that process, and what does that mean? It's very challenging. Yeah.
So there's a lot of climate risks that's just presented, but how do we communicate these risks so that we're all aware of it, and so we can all start to so it's not just like climate analysis, like analytics and
Good question. Yeah, I think a lot of it is just, public outreach. And I will say there are a lot of very skilled climate communicators out there. And I do think it's something that the media is starting to pay a little more attention to. I think you see this also in a shift with some of the rhetoric around climate change, where it's not so much that some people deny that it occurs, but I think a lot of the cleverer people who don't want to do things are shifting more towards uncertainty and things like that as a reason not to take action, versus downplaying the actual occurrence of the event itself. So I think that illustrates to some degree that things are shifting. And unfortunately, maybe it's just the coverage of a lot of these disasters and the fact that we can attribute them more to climate change that triggers that. Yeah.
So you mentioned how a lot of these problems are locally, but then we also have global problems. So I was just wondering, how does the US compare in their risk management compared to other nations when we're facing the same problems?
It depends. So the US has a much lower standard for something like flood risk prevention than the Netherlands, for example. Part of that is the history of the Netherlands as below sea level. But also it's the memory of a really catastrophic flood that they had in the 50s that, as a nation, they still kind of remember. On the other hand, Vietnam has a very low standard for preventing flooding because flooding rice crops are a really integral part of the agricultural system. So there are different thresholds that you can find codified for how much flooding that should be prevented that are different. On the mitigation side, we're not doing as much as we could, but we're also not that bad, right, compared to some other places. So it really depends. And also it depends on what your target is, right? If we're aiming for 2 degrees versus 1.5, that's a very different thing than just, are we trying to reduce, this? And so progress has to be kind of measured against that target.
How are uncertainties sort of, I don't know if this is the right word, but averaged across a matrix in order to even just create an adaptation strategy?
So how do uncertainties kind of propagate through to?
Yeah, like how are strategies, how can they even be agreed upon when there's so many varying levels of uncertainty, and like who really gets to make that decision?
Yeah, well, that's sort of the key thing about needing to engage with stakeholders and decision makers to try to get a sense of, my viewpoint is generally the more transparent you can be, the better about what assumptions went into your analysis, what are the trade-offs and potential ranges that you get, because then you allow people to kind of weigh those up. Because I certainly can't go to New Orleans and say, oh, I know what you should do, right? I don't know anything about the values of people in New Orleans in terms of sense of place, in terms of what they're willing to tolerate, et cetera. I come from the Hudson Valley, so it's a very different, thing. So I think it's just more important to be kind of illustrative and say, well, here's what we could occur, and how do you allow people to make that decision with as much information as possible, but also make it clear, what did you consider, what didn't you consider? That's always not always have to be in your analysis, but in how you frame the results when you communicate with people. That's a really important thing. Yeah.
So it seems that most of the examples you mentioned of deep uncertainties are socioeconomic, while things like equilibrium climate sensitivity is a shallow uncertainty. So I'm wondering what examples there are of deep uncertainties in geophysical aspects of the climate system, and how might we constrain them?
Yeah, I think internal variability of the climate system could be considered one, depending on the viewpoint you have. But how much do you kind of tether yourself to the observations versus simulations, right? There's also it's also one of those things where there's like the model uncertainty as well, are almost always deep. So which model do you think better captures stations, because models disagree, there's certain assumptions that get baked in. But that's a good question. I think I do generally think about deep uncertainties as being more socioeconomic typically, whereas when we typically have data that we can use to start to constrain geophysical things, but in some cases there are a number of competing hypotheses or mechanisms, and they may matter very differently for what things look like in the future. So like I would say things like there's a lot of questions related to tropical cyclone intensity that are still would fall into the category of deep uncertainty, because it's not as easy to just write down a distribution. We don't really to say, how do you think this maps with temperature increase? Yeah.
You mentioned climate risk assessment in the context of regulation and like talking with congressmen, and like how do you end up condensing the 3 different possible situations to one?
I don't. Yeah, no, that's a very good question. I don't have a good way to deal with that. I was at a workshop recently, so I think this is changing to some degree. I think there are staffers who are getting a little more savvy about uncertainty and about the way modeling kind of works. They were describing the way in which they synthesize a number of academic studies to try to get almost like a dashboard for the IRA, Investment Recovery Act. Is that the IRA stand for? The big stimulus bill, and the way in which different climate measures might move the needle. And so they were really stressing the importance of please be as transparent as possible in your assumptions, because that helps them understand which of these, how do they kind of synthesize these different scenarios together. But the way in which that helped them trade things off. So if some senator said, no, you're absolutely not doing blank, they could try to say, well, okay, can we dial up other things to try to get the same kind of aggregate impact on an estimate? So that's at least a starting point there. But no, I'm terrible at that. I kind of live in an uncertainty space, and so I'm not very good at just summarizing it.
Can you speak a little bit about how stating your assumptions and being clear about the different assumptions you're making fits in with, you mentioned at the start a bit about how you use machine learning for parts of your research. and like unsupervised learning models?
Yeah, well, so I think the key thing is that there's always different mechanistic pieces that are built in that, there's all these different dials that you can turn that may change the prediction, especially, and it's particularly important for these sort of black box models where you don't necessarily have a clean set of equations that you write down. So really saying, well, how did you do your validation versus a training data set? How did you split them? What metric did you use? What was your threshold for stop and training? Just what are all the hyperparameters that you set or didn't set if you just kind of use the default? Because all of that can impact the ending result. And then I think it's really important, and this is not always done, but there are some really good examples of it now, of doing like sensitivity analyses to really understand if you hit a particular hit your model with a particular change, what does that do to the output? And can you kind of tease apart what the difference in the predicted dynamics might be based on that?
You've touched a few times on the different disciplines that are like engaged with climate risk management. So I was wondering if there was any discipline you thought needs more people that like isn't.
I don't know about more people. I think what we don't do a very good job of is integrating across for a number of reasons. There's different norms about language, how people write papers, how people do studies, how and sometimes the incentives aren't necessarily lined up in a way to facilitate cross-disciplinary collaboration. But I think that's more of the thing is knowing, I think what's really important is having breadth and knowing how do you talk to people who are experts in other areas. You don't just go and I'm gonna use a stereotype of a particular discipline that I don't necessarily mean, but you don't just go econ-splain, right, to somebody in sociology, right, who might know something about what's going on the ground. That's saying engineers, we are very bad at this as well, right? This is a common thing. But I think just that sort of training about how do you do interdisciplinary work is something that's really essential.
Yeah, do you see, I know like some states are becoming more like climate smart and like adopt mitigation plans. So do you think these types of models are going to become like integral part of like statewide planning or more kind of
I think it's going to be local and state because it doesn't look like we're going to do much on the federal level. And it's sort of easier for states to kind of be reflexive a little bit.
Okay, I think we're at time, so let's thank Vivek again.
And if you want to follow up with any questions by email or something, I'm very happy to have this conversation.
Remember to pick up your exit cards, students, on your way out. And just drop your entrance cards.